Recording in progress.
Welcome, everyone. So we are ready to start. It's an honor to introduce Nizar Touzi, who has been a professor of applied mathematics at École Polytechnique since 2006. Previously, he was chair professor at Imperial College in London. He was an invited session speaker at the International Congress of Mathematicians in 2010. He received the Louis Bachelier Natixis Prize of the French Academy of Sciences in 2012 and the Paris Europlace Prize of Best Young Researcher in Finance in 2007. He's co-editor and associate editor in various international journals in the fields of financial mathematics, applied probability, and control theory. I've known Nizar for decades. We were in the same department in the early and mid-90s. So I'm really happy to welcome him here.
Thank you, Agnes. Thank you for the exaggerated introduction. But this means that years has passed, right? Okay, so thank you. Okay, so it's a pleasure to be here. And
sorry to interrupt. Just is there a mic? Mic. Yes. Do we have a mic?
The mic is here. I'm supposed to stick to this place, right?
Yeah, just so people that are coming online can hear you.
Yeah, that's it. The mic goes right there.
Okay, so when I thought about what I can give as talk here, I was not sure about the nature of the audience. So I gave this title of Some Problems in Financial Engineering, which means I can have time to think about it and I will prepare it at the end. And actually I prepared 4 little projects. The first one that I'm presently working on is model risk sensitivity. Then some words about mean field optimal stopping, maybe systemic risk also. I'm very excited about this project that I have been working on during the last 5 years or so. And if times allows, I will talk about another problem about battery storage mechanism design, a problem which was asked to me a few months ago, how to design market for battery storage in order to prevent from tension on electricity markets. So let's see how far I can go, but these are 4 separate problems, but you'll see that the tools are pretty much close. And basically what I want is to show you my taste of problems and to share them with you. Okay, so problem 1, model risk sensitivity. This is, I discovered this problem recently, and it's quite known in the operation research literature since the last maybe 10-15 years. People are doing what I will describe in the next slide, actually. So typically the origin of the problem is, let me take the example of pricing European options in very simple complete market models like we teach in the first year of master program. So the price is typically given as some expectation of some payoff function, G of S1. So think of 1 being the maturity of the option. G is some payoff. Think of the call option or whatever. And then you have to decide what to take for mu, for the measure, for the probability measure of the pricing. Okay, I don't want to go through discussing what is the theory which leads to this model. Let's take it like that. So we want to decide what is mu. So typically you have many problems like that. You have to choose a model. Of course, the most famous one is Black-Scholes. Black-Scholes model is just log normal. So the log of S is a Gaussian with a certain mean and a certain variance. And then you have to decide what number you are going to put for the mean and what number you're going to put for the variance. So these are the parameters of the model. Then you have more involved model, local vol model. You allow for S1 to be the final value of a stochastic differential equation, where the diffusion parameter is a function of time and space, or space here is the underlying stock price, and that is used in order to calibrate to the option market, and that provides more parameters in the model. CEV model, constant elasticity of variance. I don't write the nature of the model, but every time you choose a model, there is a number of parameters that you have to fix if you want to apply it in practice. Local stochastic vol is even more involved, more parameters, and sometimes you have to put some jumps because the derivative that you are concerned with may involve some sensitivity to the jumps. So it would make sense to put jumps in the model. So there are plenty of models, of course, because there are plenty of choices for the probability measure mu here. And from the point of view of financial engineering, you have to put numbers on these parameters. And of course, these are numbers that you deduce from observations, from data, from calibration. And so at the end of the day, not only you have to produce this what number you put on the F, which would be the price of the contract, but also you need to compute some sensitivities. What is the sensitivity of the price with respect to parameters? There is a well-known sensitivity with respect to the spot price that is used for the hedge, of course, but beyond the hedge, you also need to know what happens if I'm wrong about one of the parameters. So this is what we call model risk. If the parameter is not well set, then what happens? What is the risk that I'm taking? And we usually have the thinking that if this derivative is flat, this means that you're not taking too much risk if the parameter changes. But if it is very steepy, this means that this value of the parameter is really very sensitive. But in practice, you may have many parameters. Like in all of this model, you may have many parameters. And in fact, in practice, it's even worse than this because you have joint distributions of assets, interest rates, curves, exchange rates. So genuine use of these models in financial institutions need joint distribution of all these processes. And therefore, the dimensionality of the parameter of the model might be very high. It might be like 200 or even more. So typically, when you compute these sensitivities, you would have a vector of 100 components. And what the financial engineer would have to do is to look over this 200 components of sensitivities. What would be the worst that can happen? What is the direction of risk which is the worst? And try to understand what's going on there. So many problems appear there. So how to define the worst risk when you have 100 parameters? It's not an easy task. And how to compare? Suppose in all banks now there is model validation services, and they have to decide whether some model for some derivative is good or not. On which basis? How do I compare the use of two models? So how to compare models? This is about risk modeling again. And my criticism of this, which I'm going to address in the next slide, again, inspired from this OR literature, is what happens if you deviate from the family of models. When you compute sensitivities with respect to parameters, suppose you are thinking about Black-Scholes model, you are going to compute sensitivity with respect to the mean, to the variance. So the model may change, but still remains in the Gaussian family. in the normal distribution family. What happens? You can be very close to the normal distribution and get away from this distribution, get completely different distributions. So this sensitivity with respect to parameters does not allow to get out of these distributions. Think of if you have little bit thick tails, this is not in the Gaussian distributions, but it can be very close to the Gaussian distribution. And it's not taken into account by this kind of sensitivities. Okay, so the proposal from this OR literature is called the distributionally robust optimization. So basically, what they suggest is to, I'm writing it in a little bit more general framework. This is how far it goes in, essentially how far it goes in this literature. So suppose that the object of interest is this quantity. So I call it capital G because now it's an optimization problem over the G of X mu dx. But now I'm allowing the G to depend on some parameter. And this is minimum of a linear function of mu prime. Let's take it like that. So minimum of linear function, this is concave function. So essentially, this is a concave function. And typically in this literature, they take the set A to be compact, capital A to be compact. So it's essentially this function capital G is a concave function of the probability measure, concave and Lipschitz, because capital A is compact. So this is the typical setup. And then to address model risk, you compute the worst deviation of the quantity of interest, capital G of mu, if you deviate from the model mu with within a ball of radius r. Okay, the ball is taken in the sense of the Wasserstein metric that I call WP and which is recalled here. It's a metric on probability measures. No? Let's not elaborate more on that. It's a nice metric because it has very nice properties.
Could I think of the little r as a parameter in the density function for the distribution? Little r.
The little r is the radius of the ball. So you have a model, you decide for a model mu.
Right.
And then you say, in the previous slide, you say, what if I deviate from this model along the parameters? There are many directions in the parameters.
Like a parameter in the PDF.
Okay, no.
No? Okay, sorry.
So here you deviate along directions which are defined by the parameters of the model. So think about the Gaussian distribution. You're going to say, my Gaussian has a mean which is in neighborhood of the original mean. Okay, the variance is deviating from the variance that I'm choosing. Now in here, instead of doing that, I'm taking my model as a point in my space, in my probability space, and then you draw a ball around this point, and you take the ball of radius r. Now it's a scalar function.
I see, yes.
So my deviation now is non-parametric. I'm not saying I'm deviating along some directions which are defined by the parameters. It's a non-parametric deviations. Okay, so think again about the normal distribution. Within this ball R, you can have completely different distributions. You can produce thick tails. You can produce maybe asymmetric distributions that are not produced by the Gaussian, etc. As long as they are close in the sense of this matrix, these are possible deviations.
I see.
Okay, now the advantage of this is that now we deal with a scalar function. Capital F depends on R and measures the worst deviation. Could be inf. I'm taking soup here. If you are interested in inf, could be an inf, but same method. So we want to measure what is the worst deviation from the model that you are defining. Okay, so for me it makes a lot of sense because you really are looking at the sensitivity to the model, not along some directions defined by the parameters. And the beautiful thing is that, well, you can set up some conditions, well, in this literature, which guarantee that this function, capital F, is differentiable at the origin. And you can compute the first order correction, which means that if you deviate within the ball of radius r, this f prime of 0 by as f is differentiable is the first order correction term for this worst case scenario that is defined by this problem. And this first order deviation is as simple to compute as the option price. Because you see the formula here, you can express it in terms of LP prime norm, P prime being the conjugate of P, 1 over P plus 1 over P prime equal 1. Maybe it's better to look at it in this expression, more explicit. It's again an option price. Expected value under the same measure mu, the same measure mu that you have chosen. But now you take the LP prime norm of the derivative of the function g inside. Very simple formula. So you can, at the same time, compute the price of the option and the model risk. Compute this way, it's the first order correction. You can even go further, assuming more conditions on the function g, you can go to higher derivatives. So you can go to higher order correction terms by doing this. Okay, so this is available in the literature. And okay, some names, let me go quickly on this. And you can extend this. So in this slide, there is the first extension of this problem. Well, first, we can realize that it is not important to have this function g of this particular form. This is not important. You can have a bigger class of function g for which this method applied. By the way, I didn't say this a hat 0 is the optimizer of the problem with ball equal to 0. So this problem here. If the ball has radius 0, then there is no soup anymore. So we only need to compute capital G, and to compute capital G, everything, we have all good assumptions which guarantee that the minimizer exists. This is my I hat 0. Yes.
So it seems that your focus is on the change in the parameters, and unexpected change in the parameters. Is there a way to incorporate the unexpected change in the underlying distribution as well in this analysis?
This is, if my understanding of your question is correct, this is what we're doing here. This is what is done in this formulation. Instead of looking at the change in the parameters, you look at the change in a neighborhood of your fixed probability measure. Okay, so no parameters anymore. You forget about the parameters. You look at the ball in the space of probability measures.
Right. So what I'm saying is that if the probability measure changes, right, from one week to the next,
yes,
then I need to add another sort of dimension to this model.
It's infinite dimensional. So we are working in the infinite dimensional space of probability measures. Okay, but by focusing on the first order correction term, you can compute this explicit expression of f prime of 0. The point is to have something explicit for this correction term. Okay, and again, the p prime here is the conjugate of the p, which is the p of which defines the nature of the Wasserstein metric here.
Is it economically, what is the meaning of the payoff of the derivative being a function of a and x? What does that mean kind of economically?
Well, for one example could be if you have a portfolio optimization. Think of the problem of portfolio optimization. Then this could be expected utility of final value of the portfolio. So it depends on your investment in the risky security, for example.
And the weights, I guess the weights.
Yeah, and the A could be the weight, and this is you can think about portfolio optimization. In that case, you have this, but it can be worse. So what you could have the function capital G could be the price of an American option. Then the dependence on the probability measure could be worse. We don't know how it is, right? But it could be the whole book, the valuation of the whole book of a trading desk. then in that case, the dependence on mu can be involved. If you think about default models, CVX models, the dependence on mu can be involved. That's the interest in extending this and relaxing this concavity assumption or whatever. And here I'm considering a more general function capital G, nonlinear, but which would have some smoothness assumption. And the smoothness is formulated in terms of this definition. So I have to explain what is the derivative in the space of probability measures. Well, the only complication in here is that this probability measures is not a vector space. But we are going still, but it's a convex space, and we're going to take advantage of that. So you define the Gateau-Fréchet derivative in the sense of you compute the deviation capital of my function capital G along some convex combination of my original mu and any mu prime in any direction and normalized by epsilon. That's a directional derivative, but taken advantage of the convexity of the underlying space. And this is the definition of what I call here linear derivative, notation delta mg. So naturally, you see, by definition, I want this to be a Fréchet derivative. Fréchet derivative comes with a linear function, and the linear function is this duality product here, delta mg, duality product with the direction of the deviation, mu prime minus mu. So this means exactly duality product with probability measures. This means exactly the integration of this function with respect to mu prime minus mu dx. So in fact, the delta mg is a function of the underlying measure mu, but also it introduces an x here, which is in the underlying space. So delta mg, remember that delta mg is a function on the space of probability measures times the underlying space. While g itself is a function on the probability measures to R. Okay, by going to one derivative with respect to measure, you are creating this dependence on RD, which is very natural. Think of finite dimensional. If we were in a finite dimensional space, then the gradient becomes a vector, right? So this now we are in infinite dimension, the gradient becomes a function, right? Okay, we're going to use this definition later, and we have similar formula as before. The first order correction now for this problem, well, you need to compute this linear derivative, and then to compute its derivative with respect to the x variable, and take the LP prime norm. Of course, I'm not putting any assumption here, but you can imagine what kind of assumption you have to add. You need to guarantee that these derivatives exist, at least in a weak sense, to compute these integrals with respect to mu, and you need to compute it. So you need it to exist and also to have enough integrability to compute this LP prime. But these are just details. Okay, second extension. In financial applications, we usually have this martingale constraint. If you want to think about models are arbitrage free in frictionless markets. So how to incorporate this? Because you want to deviate with respect to the model, but at the same time, you don't want to consider models which admit arbitrage. So let's suppose that, I'm saying this for Steve, just suppose that you care about models without arbitrage. You can discuss that, of course. You can argue on that. But let's suppose that you want to compute the first order correction, but you believe very strongly and firmly that you can only visit models which are free from arbitrage. Then you have to correct for that when you visit the neighboring models. So you can do that. Well, first, I'm recalling here that no arbitrage condition is essentially martingale condition on the underlying model, which means if you have just a one period model, expected value of the value of the underlying stock S1 is equal to S0. If you have a dynamic model, S1, Sn, then this is the martingale condition. Conditional expectation, conditional to the past, produces the current value of the process. And I'm recalling very quickly for those who are not familiar with this connection that this is due to a very simple idea. The reason is that if you take any strategy of this sort, H times the difference Sn minus 1, where please notice that the H depends on the past values of the stock because it depends on the information. This is a strategy that you decide at time n minus 1. So you can use all the information available at time n minus 1, which is here, the path of S until n minus 1. And this has cost 0 because you pay at time n minus 1 this H times Sn minus 1, and you collect at time n the value at time Sn. I'm assuming that interest rates are 0. I didn't say it. No interest rate, everything normalized with interest rate equal to 0, or think about discounted quantities. So this is, I hope it's clear for everyone that this is a costless payoff, because this says that you buy the quantity H at time n minus 1 at the price Sn minus 1, so it comes with a minus, and you collect the same quantity at price Sn. So zero investment, so 0 cost. And 0 cost by no arbitrage means that its price has to be 0. And the price is this mu of this quantity. But if you compute this equal to 0, and you consider the fact that H is arbitrary, then this exactly means that this is exactly the definition of condition expectation. This is exactly the martingale condition. So it's very easy to understand the connection between no arbitrage and this martingale condition. Okay, now back to our problem. I would like to now restrict my deviations to the ball, same ball, Wasserstein ball, around the measure mu with radius r, but now intersected with martingale models. I only want to deviate along martingale models. That's also possible, and you can prove here under some conditions, again, that I don't write explicitly here, that you can produce this first order correction term under the martingale condition, which is now the infimum over all functions h, which are continuously differentiable and bounded on the underlying space of this quantity here. And for p equal 2, you can go further, and you can characterize the optimal h by a Fredholm integral equation. Actually, the direct characterization that you obtain is by a second order ODE. But it turns out that there are some quantities which combine very well, and you can convert the second order ODE into an integral equation. Anyway, this is all what I'm going to say on this example. Probably one can do better, but this is really a fresh project, and maybe one can do more beyond p equal 2, beyond dimension 1. Anyway, I'll stop there. This is one first problem that I consider to be interesting about this risk model. Well, the interest is that it's not more difficult than computing the Greeks derivatives, because the formula is very simple. Okay, problem 2. Problem 2 is mean field optimal stopping. Optimal stopping for financial applications is related to, well, American options, of course. Everybody thinks about American options. American options, well known. I'm not going to redo the theory. To review the theory, American options are about find the best time to exercise the option. So the option here has a payoff phi of x. So you want to find the best time to exercise the option. And therefore, for the seller of the option, he's going to assume that he has the most clever opponent against him, and therefore he has to charge the worst price. Okay, of course, this can be proved, etc., and well known. Okay, and these are soup over stopping times, not deterministic times, because the structure is like that. Let me put it there. This problem is well known in probability, in applied probability, and usually applies to the typical example is about choosing a candidate among some applicants. If you have capital N applicants, this is how we teach it to Master 1 students. If you receive capital N applications, which are independent, and capital N is large, when do you stop seeing candidates? At some point you say, I'm not going to run through the million of candidates. At some point I will stop. And the famous solution of this problem is that there is a precise number of candidates, 37%, after 37 point blah, blah, blah. After 37, you can sleep for 37% of the applicants, not completely sleep because you have to watch out what is the level of candidates. And then after the 37% first candidates, you choose the best, the one which is best compared to this first 37%, and then you can stop. According to this criterion, this is optimal. Okay, American option or optimal stopping, typically with continuous time models, are related to partial differential equations, obstacle problem. Well-known obstacle problem in this case is if the underlying process X is defined by some stochastic differential equation. I'm recording the generator here because I'm going to use this notation. So the generator is drift multiplying scalar product with the gradient plus squared diffusion matrix multiplying the Hessian, 1/2. Then what you can prove is that the solution of this problem is the initial value, little v, small v of 0x0, where v is defined as the solution, is characterized by some PDE, and the PDE is what we call the obstacle PDE. It's the heat equation, minimum of the heat equation with this v minus g equals 0, and g is called the obstacle in this literature. We can also formulate a probabilistic characterization which extends this to the non-Markovian case. This is so-called Snell envelope theory, but I don't want to go through that. Okay, so remember, to solve this optimal stopping, you have to record, this is what you get from the generator, A, time derivative, and then the minimum of this with a minus sign, v minus g equals 0. In particular, minimum equals 0 means that each item of the minimum is non-negative. The blue part being non-negative, this means that v is greater than g. Of course, because if you look, oh, g should be phi, I'm sorry. The v and the, so the phi and the g are the same. So v greater than g, yes, because immediate stopping is legitimate. You can always do at least as good as immediate stopping. This is the v greater than g, minus dtv minus av, non-negative. This means that v of txt is a super martingale. So that's the Snell envelope theory. And then the minimum means that, well, either you stop the first time that you hit g, and that's the optimal stopping expression here. Optimal stopping is the first time that you hit the obstacle. Okay, well-known theory. Now I want to extend this to what if you have many positions? In this example, you have one position and you receive capital N applicants, and you look at them independently one by one, and you cannot reject one and call him back. Once you reject, it's finished. What if you have many positions, 10, or I don't know, maybe for a big company, much more? Then you know that, then you see that hiring, let's think about department hiring people, let me say about mathematics, for example. Math department hiring 3 people. So typically, if the first person is hired in, is an expert in PDEs, maybe you can consider that the second person would be hired in probability. And maybe the third person would be hired in data science today. Of course, we have to hire in data science. So you see that the 3 hires are connected to each other. You cannot separate the problem. You cannot say 3 the hiring 3 people is the same as taking 3 different committees and asking them to hire one by one. That doesn't make sense. You want to think about the department. We need different people because we have to teach different courses or to have to different research, etc. So now the problem is, what is the best time to stop? But now you have to stop for each position, tau 1, tau n. Now you have x1, xn, n processes. And then you have nonlinear function phi here. If phi is linear, then this is obvious. This can be obviously converted to n problems with separate problems. You can separate the stoppings. But if phi nonlinear, then it does not separate. Okay, so how to solve this problem? Let's think about the 2 particles problem. Two candidates. We go back to this example. In the 2 candidates example, if you think for 2 minutes about this problem, then you can realize very quickly that it can be converted to the problem of optimal stopping of one single optimal stopping. And the idea is that in order to stop the process for the 2 jobs, you first have to make one first decision is, when do I stop one of the jobs, one of the processes of one of the jobs? Okay, that's the minimum between tau 1 and tau 2. That's step number 1. And once you decide that you are going to stop one of the processes, you choose, do I stop by taking the probabilist or do I stop by taking the PDE person? Okay, so by doing this, I'm converting the problem of stopping the 2 processes into several problems of stopping each one of the only one stopping process. So precisely at tau 1 minimum with tau 2, there are 2 possibilities: either tau 1 less than tau 2, and which means that you are going to stop the first job, the process for the first job, and still continue to search for the second one. So you have to freeze the x1 process at the value tau 1 and still search for the when to stop for the job number 2. Okay, and similarly, if tau 1 is strictly greater than tau 2, then you are going to freeze the second job. You're done for the second job, and you choose when to stop for the first job. Okay, so at the end of the day, you have to compute, you have to handle 3 optimal stopping problems. The optimal stopping problems for each of the particles, V1 and V2, with the other particle stopped, with the other process frozen. And then once you solve these problems, you compute the maximum of them, and you solve again another optimal stopping problem, where you stop only once with reward process given by the maximum of the 2 reward process of the single optimal stopping problems. And this solves the problem with 2 particles. Okay, and reduces back to the original problem. Of course, you can extend, and you can figure out that if you have n processes to stop, then you can iterate this argument. First, the problem of stopping each of the particles, that's a single optimal stopping problem. Then the problems of stopping the particles 2 by 2. There's a lot of them. This is combinatorial now. Okay, once you know all of the stopping of one single particle, you can go to the 2 by 2. Once you know all the possible 2 by 2, you can go to the 3 by 3, etc., etc. It's combinatorial. So it gets very involved, but it works. You can prove that this produces the value function, reduces the problem of multiple optimal stopping to the problem of one single optimal stopping at each time, but many of them. Okay, so my interest now is this is a high dimensionality problem. Complexity is very high because it's combinatorial. So when n is large, I would like to see what happens when n goes to infinity, mean field limit. I would like to see when the mean field limit of this problem. And then I'm going to look at some scaling limits. And therefore, I'm going to specialize the discussion to the case where this reward processes x for each particle n is defined by this type of stochastic differential equation. So tau n is the time when you're going to stop the reward process n. Okay, so now this is the optimal stopping problem or American option for a book of American options. You have a book of American options, how to exercise them. If your criterion is, for example, the value at risk of the book, if you want, non-linear criterion. If it is linear criterion, then again it's separate. Okay, so symmetry here is, or anonymity, if you want to cut like that, is defining these particles to have similar dynamics. So you see that the B does not depend on n. The dependence on n is only through the xn here and the x0n. So they have different initial condition. And then the dependence on n is only through the xn. And the dependence on the others is symmetric, only through the distribution. This is the empirical distribution. Delta is for the Dirac mass. Okay, so this is somehow a dependence of the dynamics of the particle through this function b, again, which is not dependent on n, but depends on the other only through the distribution. You don't want to know who is who. There are some particles, and you only need to, suppose you want to make your way through some crowd. You don't want to know, oh, Amin is there. I don't want to pass through that point because I really hate him. I don't want to say hi, right? You just see distribution of people and you make your way through places where you are comfortable, right? You don't pay attention what are the names. So this is the meaning of this statistical dependence on the others somehow. Okay, and we do that on purpose. Of course, we are restricting the model, but on the other hand, now we are going to take limits, and you can see where I'm coming. This is converging to the marginal distribution of the limiting process, and this is well-known Makin-Vlasov stochastic differential equations, except that here the new feature is that these Makin-Vlasov stochastic differential equations are stopped. So these are stopped Makin-Vlasov stochastic differential equation in the limits. Okay, so again, some notations. I'm taking the Brown emotions here to be all independent. Well, technically, this is very important because if there is dependence, then there will be this empirical distribution would converge to the conditional distribution, conditional to the common noise, if there is a correlation through some common noise. Here we're making it simple. The Wn are all independent, and therefore this empirical measure will be converging to the marginal distribution, which is deterministic object, makes things much easier. And then I'm going also to introduce some marking of the particles. I'm going to introduce this I index. So I is a vector of ones and zeros, which indicate whether the corresponding particle has been stopped before or not. I equals 1 if the particle is still continuing, and equals 0 if it has been stopped and then frozen. Okay? So you can prove that if you add this state, now the position of the particle is the vector x of all particles, x1 to xn. X is the position of the particle. And this I variable says that the particle still needs to stop or not. If you take this pair, then things are turned into a Markovian problem. And you can apply this optimal stopping theory. And typically, you have this involved obstacle equation, which we can explain. This is the generator of the system. dTV, and then the generator, because of independence of the Brownian motion, these are the sum of the individual generations. There is no correlation in the Brownian motions. So reduces to the sum, but you only take the generator of those particles which are not stopped. Those which are stopped, so those whose IN is 0, you don't take the generator anymore. They don't diffuse anymore because they're frozen. Okay, so this is the reason for this sum here. And now if the particles are in the state I, the obstacle, if you stop one of the particles, what happens is that you are going to move us to a situation where one of the ones is turned to a 0 in this vector of i's, right? And this is my notation of I prime less than I. So this means this is in the lexicographic order. All components are all that way. And the strictly less means that one of the components is strictly less than the corresponding one. So this is exactly applying the previous theory with one single optimal stopping. Okay, now question. What happens when n goes to infinity? Huh? How am I doing with the time? Maybe I should keep my phone here. So the question is, what happens when n goes to infinity in this problem? Well, when n goes to infinity, you can see that for this sum, you can guess that probably I should expect some law of large numbers. But these are PDEs. Of course, we have to make sense of this. Huh? I'm expecting some law of large numbers here. But for this max, when I saw this problem in the beginning, I was very curious. What happens to the max when n goes to infinity? Okay, so I was very curious. I see that you're as curious as me. So question is, what happens for when n goes to infinity for the problem value function, for the optimal stopping strategy, and what happens to this PDE? Obviously, I don't have much time to analyze all these aspects, so I will go very quickly to the way that we solve this problem. So the trick here is to go to the natural limiting problem. So I'm not proving that this is the limit. I take the natural limiting problem, and once I can analyze the natural limiting problem, I can prove that it corresponds to the limit of the finite population problem. This is a trick in these problems. The natural limiting problem is, again, now I use I for the process which was the vector in. Now I use the same letter, capital I. So capital I is 1 if tau is greater than s, so the particle is still living, is not stopped, and 0 after that. So this is my I. This is exactly my definition from before. Dynamics of the process, same as before, but I am replacing the empirical measure by the law. Okay. It's classical in this Makin-Vlasov literature that we would have convergence, but here it's a little bit different because of the stopped diffusions. We have stopped stochastic diffusion. So I'm guessing that this should be the natural limiting underlying process. And now I define a stopping strategy as a probability distribution on a joint between the x tau and I tau. It's the joint. Okay, so I am allowing for mixing strategy because I'm taking joint distributions. I'm not saying if x is at such position, then I stop or not. Here, if x is at some position, then I may flip a coin and decide whether to stop or not. And in fact, the nature of the problem is like that. If you think about it, the nature of the problem is like that. Take an example of you go to the beach. You like the beach, right? Barry has a beach house. You go to the beach and there's a lot of people. So at some point, it's very crowded. And then you decide, should I stay or not? Right? There's too much people. Should I stay or not? Okay. If it is pure strategy, then at some point, everybody's going to leave at the same time. Okay. But that is not in the nature of the problem because Maybe if half of the people leave the beach, then you're better off, you stay, right? So randomized strategy. It's the nature of the problem. And actually, when you solve the problem, you find this randomized strategy. So mean field control and optimal stopping have special features like that. Okay, this is what happens. You can, once you write with these variables, you express everything in terms of probability measures. You can write the value function in terms, the arguments of the value function is time and probability measure. So we're back to the analysis on the space of probability measures, which is the common factor of the examples that I have chosen. And then you can follow the natural, if you're familiar with stochastic control, this is a control problem. You need to write what we call dynamic programming principle for those who are familiar with this. And yes, of course, knows this. Then once you have this dynamic programming principle, the remaining task is to use differential calculus and get a PDE for this. Okay, differential calculus. Differential calculus here, it's, what do we have? We have to look at the differential of V, dV, along the law of this stochastic differential equation. Okay? So it's not completely Ito's formula. It's an Ito formula, but on the law of the stochastic differentiation. New question. Ito formula along the law of the stochastic differential equation, not along the solution of the stochastic differential equation. Okay, that we can do. And the result is this. I don't expect to understand what's going on. Only one remark. I put this slide just to show you that in this Ito formula, you have this L double bar U. And if you look at the definition of the L double bar U, it's DTU plus expectation of the generator applied to the derivative. Okay? And this explains, this is very consistent. This is in agreement with this blue quantity. We have a law of large numbers which comes with this AN. Now, this is the meaning of once you have a good scaling, 1 over n, sum I from 1 to n of this, then this was expected from the beginning. So we have this A double bar, and now we know where it comes from. It comes from this Ito formula. Okay? And once you have Ito formula, it's just follow the usual way to get a PDE. I'm not going to go through that. Main results from dynamic programming principle, you can produce the analog of the obstacle equation, which is the PDE associated to that infinitesimal version of this dynamic programming principle. And you can prove that you have a unique solution. So this equation would characterize the problem. We have done viscosity solutions to bypass regularity issues. And more importantly, we can prove that the finite population problem, now we go back to our original problem, which was finite population problem, converges to the limiting mean field problem. The strategies converge, etc., etc. And this is what we call chaos propagation. And in this case, it's chaos propagation with optimal stopping and with stopped stochastic differential equation. Okay, we're presently working on the numerical approximation aspect using deep Galerkin methods because, as I showed you in the beginning, the natural naive way of approaching the problem is very combinatorial. So it explodes and it is hardly applicable. Okay, I still have how much? 5 minutes, right? Is that my time?
That's fine, 5 to 6 minutes.
Oh, 5-6 minutes. I prepared this slide to show you that Ito formula for flows or stochastic differential equation, you should not be impressed by that. It's very easy. I like to show this because in the standard literature, there is a very thick book by Cremona and Delarue. These proofs are horrible because you have to go back to the finite population and in the finite population problem, you go back to the standard Ito formula because this is 1 over n sum of xi's if you want. Then you go back to the standard Ito formula and then go to the limit. So use chaos propagation, blah, blah, blah. It's a lot of work. But in fact, there are very easy proofs. The easy proofs is to go back to our definition of derivative, delta m, which is, you can write it by as u of mu ti minus u of mu ti minus 1 equals this right-hand expression, which is exactly our definition with the directional derivative. And the only thing to remark is that what is in here, as mu ti is the law of xti, mu ti minus 1 is the law of xti minus 1, this is the expected value of this difference. Now this difference, this is a function of x. Just apply standard Ito formula. No problem. And can be extended to all situations that you have in mind, jump processes, even if there is common noise, conditional distributions. Okay, let me stop it there. 3 minutes. No, you want to stop here? Okay.
Is there any question?
Yes.
Maybe you can give us a quick summary of the next application, maybe just in plain English.
Yeah, 3 minutes. This is 3 minutes about systemic risk. What I have done in systemic risk. So basically what we want is to substitute to the standard cap M a model where there is an interaction between agents of firms. So again, population of firms which are connected to each other because they hold each other. They hold each other by equity or debt or whatever. I'm going to focus on equity. Okay, let me go very quickly and maybe present the simplest example. Suppose you have two firms. Maybe the pizza place, pizza restaurant, and ice cream place. Okay? Each one has its own risk, which I call PI here. So if they don't talk to each other, their value is exactly defined by this P0, P1 processes. Now, suddenly they realize, oh, what if we diversify mutually our risk? What does that mean? I can hold 30% of the equity of the pizza place if I'm the ice cream place, which means that whatever profit and loss is going to incurred by the pizza place, if it's profit, I will have 30% of the profit. If it's losses, I will have 30% of the losses. Okay? So if I do that, then firm 0 holds a proportion P01 of firm 1. And therefore, the equity of firm 0 is affected by this holding. So adds up 30% of the profit or losses of firm 1. Again, the dx1 here can be positive or negative, profit or losses. Okay? Similarly, firm 1 can do the same. Okay? The ice cream place can decide to hold 37% of the pizza place, because in case the pizza is doing well, it will take advantage of that. Okay? And then we have this system which describes the profit and losses, or if you want, the value of each one of these agents. If you have n interacting firms now, there are more firms. If you are in Manhattan, there is a lot of interacting firms, and they decide to diversify their risk. This thing extends naturally. So dxi equals first dpi, and then whatever ith agent gets from holding the other agents, and gives up whatever the other agents holds of it. Right? Very natural dynamics, and we want to understand what can we prove existence of an equilibrium of this game? Nash equilibrium. Nash equilibrium means that each individual maximizes some criterion, and then they have to agree. Okay, in 3 minutes, let me discuss it very quickly. Well, you see there are sums. Sums, then law of large numbers. You think law of large numbers. After, if you have a good scaling, 1 over n, typically, then you expect that this sum here can be replaced in the limit by expected value. So same strategy as before. Let's go to the natural limiting model, solve the natural limiting model. And once we know things about the natural limiting model, we go back to the finite population and we show convergence. This is the approach. So here, each of the summation, you can guess what it converges to. And this is what you get as a model. In the limit, the suggested model has this form. So it's very strange. The hat stands for independent copies of X. So the control is beta. This is how much you hold the others. I switch it from pi to beta because it's too complicated to, if you put pi here, you have to think pi of xi as j, pi of xj xi. So I call it beta because the ith agent controls beta, given pi. This is the Nash equilibrium. Okay, then you end up with this type of dynamics for the representative firm, representative agent. DXC has this representative dynamics. And the question is, what is the best beta, given that the others play pi? First, and then can we find a pi so that if the others play pi, the optimal beta also is consistent with pi, Nash equilibrium. One more detail at default, because if you want to talk about systemic risk, then you want to say, oh, what happens for default? Can I, in this system where everybody holds each other, can I prove something like defaults happen more often or less often? Is it more risky, systemic risk? What's going on there? Okay, so I add this default by defining default as the value as happening when the process hits zero. So when the equity is zero, done, dead, disappears, right? Okay, so this is the definition of Nash equilibrium, and now we can solve this problem. Now it's a mess, right? Everybody optimizes its own strategy, and maybe we can find an equilibrium. Well, for this problem, there is an explicit solution, which is expressed in this slide, and which says that in 20 seconds, it says that the equilibrium distribution is given by this stochastic differential equation. So you start from little b and little sigma for the idiosyncratic risk, and you end up at equilibrium with capital B, capital sigma, which are given by these expressions with this C0 and C1. The only thing to compute is C1, which is solution of this integral equation. Can prove that it exists and is unique. And the optimal strategies at equilibrium is to hold only those particles which have positive drift. You only hold those particles which have positive drift, and you disregard the others. Don't hold them. This is one equilibrium. We don't know how to prove uniqueness. So typically, what you see here is that volatility sigma gets smaller because it's even sigma if the indicator function is zero, or it's sigma divided by a number which is greater than one. So somehow, so in this model, as expected, the cross-holding at equilibrium stabilizes the system. There is less volatility. As for the drift, there is an averaging effect. Okay, maybe I'll stop here. I can go forever talking about these problems, but I think it's enough. Thank you very much.
Strikes me that one interesting application of this is that, in the sort of finance literature, you think about solving problems, strategic problems, by owning the equity of other companies. That, to the extent you have externalities or, legal ways to get around these kind of competitive problems, you can solve them by having joint ownership across companies. And I was just thinking, I don't know if it's relevant to this at all, but is there a way to think about this in the context of the strategic value of the ownership of these companies, in addition to the sort of properties of the this problem? What if there was an extra value to, in other words, owning a,
What is the extra value from
Yeah.
from holding the others?
Yeah.
Huh? Well, you see, one of the effects is that overall, the system is stabilized by this diversification. So it's good for the system,
that's what I'm
right?
thinking.
Which was not,
Yeah.
which was cannot predict in the beginning, right? Well, we feel like risk diversification. So intuitively, it's better to ensure ourselves, right? But in this simple model, you really find it as a result. At the end, the diffusion is for those particles which have negative drift. So these miserable particles that nobody wants to hold, they get the same diffusion. For those particles who have positive drift, they get more stability. Okay, but the miserable particles may recover because this is stochastic system. There are Brown emotions there, so they may recover and have positive, eventually have positive drift and so on and so forth. Huh? Well, what I don't show you is that in this model we can compute the probability of default, and we can have an equation for the diffusion, for the evolution of the probability of default. But that needs.
I have class after.
Yeah, sure.
I'm sorry.
Thank you.
Sorry to interrupt. Hi, Steve.
I have a comment. So maybe the reason why the bad particles can become like a good particles and vice versa is because I think here we're omitting that we have a central bank behind the scene that controls those banks by setting, I don't know, like a maximum cap. And each bank which is positive now at time t, it's beyond the cap, then they have like some extra money that can put in the market, so the bad companies can buy. But if I buy too much again, then the bad becomes too good.
Yes.
The good becomes too bad, and it's just like a game like this.
But this is something that you have to add. In this model, there is no external, but it's very interesting. It would be very interesting in terms of regulation. So your idea is, can we put up, in addition to this Nash equilibrium, some regulator which sets conditions in view of minimizing the probability of default or something like that? Yes, that's a very good idea. And
Plot here, is it like in the asymptote regime, or is it like in the limit, or is it like we have phase transition, or is it just we have this formula for any time?
This formula is when n goes to infinity, huh? And you can prove that once you solve this, you can prove that you can find a Nash equilibrium for the finite population problem, which was very difficult to find. In fact, you can find an approximate Nash equilibrium. The precise mathematical statement is put here. Approximate Nash means that every agent is almost at its maximum. You can find explicitly a strategy which uses the solution of the limiting problem, the B from the limiting problem. By using the B from the limiting problem, you can prove that this strategy is almost optimal for the N population problem. This is what you can prove. Well, this is a nice thing about this mean field model, allows you to have approximate finite population equilibrium solutions. Thank you.
That's locked out.
This is way out of my normal range of understanding, but isn't changed, that the way you've shown here is that there is, there will be.
He didn't get to give them their cost as well, when he went back, so.
And,
Do they get tips on
They-
most typically?
I don't know.